In this presentation, we are going to look at the first part of Chapter 2, Elements of Probability. Let's start with identifying some keywords. The first keyword is experiment. Any process or observations or measurements that has well-defined set of outcomes is called as experiment. There are two different types of experiments, the deterministic and probabilistic. The experiments that we conduct inside laboratories to verify the law of science or establish laws of other areas are called deterministic. For example, an experiment that we conduct to verify the Newton's law of motion is a deterministic experiment. In deterministic experiments, we already know the outcome of the experiment, but we conduct it to verify the certain law. On the other hand, probabilistic experiments or random experiments are the experiments whose result is uncertain, which means we do not know the final outcome until we perform the experiment. There can be more than one possible outcomes, but the answer will be only one of them. For example, if we toss a coin, we know that there are two possible outcomes, head or tail, but until we finish the experiment, we do not know what will be the final outcome. Hence, the second keyword is the outcomes. The results obtained from an experiment is called an outcome. They can be instrumental readings, or they can be counts, or they can be values obtained through extensive calculations. For example, if we measure a weight of an object and then the time it traveled and the distance, we can measure the weight, the distance, and the time using relevant instruments, and then we can calculate the speed and the acceleration. Now, if we think about an experiment of tossing a coin, you may end up with getting a head or a tail. If you did not, getting a head as yes and getting a tail as no, if we toss the coin 10 times, you will end up with a certain number of yeses and a certain number of no's. The third keyword is the sample space. The set of all possible outcomes of an experiment is called the sample space. It is usually denoted by S or omega. Each outcome of a sample space is called a sample point. If a sample space has a finite number of elements, we can list those elements using the usual set notation. As an example, think about tossing a coin. Then we can write the sample space S in the set notation. That means all possible outcomes within curly brackets as H or T, where H is getting a head and T is getting a tail. So this is the sample space of the experiment of flipping a coin. A sample space with a large or infinite number of elements is best described by a statement or a rule. For example, if the possible outcomes of an experiment are patients having leukemia, we can write the sample space as X such that X is a leukemia patient. So we rate this as S is the set of all X such that X is a leukemia patient. Similarly, if X is the set of odd positive integers, we can write sample space as S is 2k plus 1, where k can be 0, 1, 2, and so on. How we formulate the sample space for a given situation will depend on the problem at hand. If an experiment consists with one roll of a die, we are interested in which phase is turned up, we would use the following sample space. We can write S as one of the outcomes 1, 2, 3, 4, 5 and 6. However, if I am interested only in whether the phase turned up is even or odd, then our sample space will be odd or even. So you can see the difference. The same experiment, according to the way we formulate it, you will end up with different sample spaces. Now describe a sample space that might be appropriate for an experiment in which we roll a pair of dice, one red and one green. How do we write the sample space of this experiment? We can denote the sample space as a pair X and Y, where X is the outcomes of the red dice and Y is the outcomes of the green dice. Or else, a second sample space can be defined as the total of the two numbers turned up by the two dice. So, the possible outcomes will be 2, 3, 4, up to the maximum 12. Because if we add the faces turned up by the two dice, the minimum will be 1 and 1, which is 2, and then the maximum will be 6 plus 6, which is 12. Sample space can be classified as finite if it contains finite number of elements. S1 and S2 are finite sample spaces. So in the above experiment, if we denote this as S2 and S1, we can clearly see that S1 and S2 are finite sample spaces because it contains finite number of elements. If a coin is flipped until a head appears, then we will get our sample space like this. You may get the head in the first flip, or maybe in the second flip, maybe the third flip, maybe the fourth flip, and it may go until infinity. This is an infinite sequence, which means it is unending. We flip the coin until head appears and we do not know in which flip that the head will appear. But the number of elements in the sample space can be identified distinctly, hence we call it a countable sample space. If a sample space contains finite number of elements, but the elements are countable, then it is said to be discrete. On the other hand, if outcomes of an experiment are neither finite nor countable infinite, it is said to be continuous sample space. They arise in practice whenever the outcomes of experiments are measurements of physical properties such as temperature, speed, length, and so on. These are measured in continuous scale. The next keyword is event. Any event can be identified with a collection of points which constitute a subset of a sample space. So simply, an event is a subset of the sample space. We represent events using capital letters. For example, if we refer the sample space which we obtained by rolling a 6-sided dice, we can define an event A, which is the number of points rolled with the die is divisible by 3. Then our event A can be written as 3 and 6, because only 3 and 6 in this sample space are divisible by 3. Now let's go back to the example of rolling a pair of dice. Let's define an event B as the total value of points rolled with the pair of dice is 7. It is easy if we note down the sample space in a manner like the points x, y as x as the first dice and y as the second dice, and we know the possible outcomes of x and y. So writing the sample space in this manner, it's easy to figure out the corresponding events. So the first outcome will be 1, 1, then 1, 2, 1, 3, so on up to 1, 6. The next set, 2 from the first die and 2 from the second, and so on, 2 from the first and 6 from the second. Likewise, you can fill this grid up to the last outcome. So you'll end up with 36 possible outcomes. In the diagonal, you have the same value for both dice. Now it is easy to figure out the events. Okay, event B is the outcomes where the sum of the two dice is 7. Let's try to find the points or pairs where you end up with the sum as 7. We can have 1, 6, 2, 5, 3, 4, and then 4 from the first, 3 from the second, 5 from the first, 2 from the second, 6 from the first, 1 from the second. So in all these 6 pairs, you will get the sum to be 7. Okay, let's try to find another event. Event C is defined as the total of values less than or equal to 5. Which means if you add up these values, you will end up with the sum to be less than or equal to 5. Okay, let's try to fill a few more points. If you look at these pairs, you can see that 1 and 1, 2 is less than 5, 1 plus 2, 3 is less than 5, and 1 plus 4, that is 5. So our event C is the points where the total is less than or equal to 5. So you will end up with the points in this area. So this will be your event C. So if you want, you can list down these events one by one, and you will end up with 10 possible outcomes in your event C. So they will be 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and finally 4, 1. I hope this is clear to all of you. Let's look at another example. Now consider an experiment of tossing 3 coins at the same time. And you are observing the phases of those 3 tosses. So let's define A as getting 2 heads from the experiment, B as getting 3 heads from the experiment, and C as getting at least 2 heads. Before we answer these questions, we have to find the sample space of this experiment. We are tossing 3 coins, so we will end up with all 3 heads, head, head and tail, head, tail, head, head, tail, tail, and so on. If you look at the all possible outcomes, you will end up with 8 of them. The knowledge you got from permutations, combinations, that will help you in identify the number of possible outcomes that you will get by tossing 3 coins. So you can make sure you do not miss any outcome. Okay, now we have the complete sample space with us. Let's try to identify each of these events. Event A is getting 2 heads from the experiment. So you can see the second one, third one, fifth one. So those are the elements in event A, getting 2 heads. Okay. What about event B? That is getting 3 heads from the experiment. We have only one, which is H, H, H. Third one, getting at least 2 heads. That means the least will be 2, but it can be more. That means we can go up to all 3 heads or 2 heads. So there are 3 different combinations where you can get 2 heads. So this will be our event C. Okay. The next example is a little bit different. We want to construct the sample space for the lifetime of a CFL bulb and indicate the event F as the bulb fails before the end of 12 months. So let's define T as the lifetime of the bulb. So our sample space will be T such that T is greater than or equal to 0. T is the lifetime. Lifetime is never negative. It can be 0 or more. So this is our sample space. Then our event F is the bulb fails before the end of 12 months. So that will be T such that T is in between 0 and 12. So T measured in months. Now in many of these problems of probability, we are interested in the events that are actually combinations of 2 or more events, which means the union, intersection, and the complement. If A and B are any 2 subsets of the sample space S, their union, which we denote as A union B, is the subset of S that contains all the elements that are either in A, in B, or in both. We can easily explain the union using a Venn diagram. So in a Venn diagram, our sample space is denoted as the rectangle, and inside that we denote the events using circles. So let's say this is event A and this is event B. The union of A and B will be this colored area. So it contains elements either in A, in B, or in both. Both is where this overlapping area. The next is the intersection of A and B. Now if you go back to the union, we refer this as A, O, B. Next is the intersection. The notation is A intersection B, that is the subset of S that contains all the elements that are both in A and B. We denote it as A and B. So that is the overlapping area. That is the area where you contain elements in both A and B. So here's our sample space. The circle for A, circle for B. And if you color the overlapping area, that is the intersection. So this area is the intersection of A and B. Then the complement of A, which we denote as S complement or A prime. So another notation is S complement. That is the subset of S that contains all the elements of S that are not in A. Or we sometimes called it not A. So here's the sample space and we have our event A. Then A's complement or not A is the area which is outside A. So this is A's complement. We say two events A and B in a sample space is mutually exclusive if there are no elements in common. Sometimes we call them disjoint events. So if we draw the events inside the sample space, they will not have any overlapping areas. So A and B are disjoint events, or they are mutually exclusive. Therefore, the intersection is empty. Another one is A contains in B. So that means A is a proper subset of B. So which means we have the circle for B and A is contained within the circle B. So this is called as A contained in B. Okay. Finally, let's look at a complete example and try to identify the complement, union, and the intersection or the combinations of these possible outcomes. Suppose for a random experiment, the sample space, event A, B, and C are defined as follows. Our sample space S contains the letters A, B, C, D, E, F, G, and then you have event A, B, and C. So let's try to find these sets. In part A, we have to find the complement of A, which means all the elements in S but not in A. So A has A, B, C, and D. The rest will be E, F, and G. Now if we compare A's complement with C, they are the same. So A's complement is exactly C. What is B's complement? B contains A, C, E, and G. So the remaining in the sample space, that will be B, D, and F will be B's complement. Then C's complement will be A, B, C, and D, which is exactly A. Now let's try to find the union of A and B. That means the elements in A, elements in B, or in both. Since we are using set notation, we do not use repetitions. Therefore, the A union B will be A, B, C, D, E, and G. So A, C are appearing in both, but we do not write it twice because it is a set notation. So you'll end up with the union of A and B. The next is the intersection of A and C. If you look at A and C, they are complements of each other. They do not have any item in common. So A intersection C is an empty set. The next one is the B union C. Okay. So the elements in B or C or in both, we will end up with A, C, E, G. E and G already here, so the last one, F. The next we need A intersection B's complement. How do we find that? If we draw the Venn diagram to represent A intersection B's complement, it will be like this. So you have A and B. If we write down the elements within A and B, we will end up with, let's start with filling the inside or the overlapping area. They will be A and C. Then for A we have B and D. For B we have E and G. Outside these two circles we have the complement of the union of A and B, which will be F. Okay. Now what we need is A intersection B's complement. That means the elements in A, elements in B's complement, and their intersection. So the intersection will be where you have the pattern, these crosses. So if we look carefully, they will be only B and D. So A intersection B's complement will contain only B and D. So another way to represent this as the elements in B but not elements in A but not in B. Okay, so that will be simply the area where you have elements in A but not in B. So you have only B and D. The next one is the complement of A union B. The complement of A union B. So you see the complement outside this union. We already have A union B. The complement will be the rest of the elements in the sample space but not in A union B. That will be only F. The next one is A's complement intersection B's complement. Okay, so we have A's complement here in part A, B's complement, and their intersection is the common elements, and we can see the common element is only F. Now if you compare the answers in F and G, you see that A union B's complement is same as A's complement intersection B's complement. In the same manner, if you find A intersection B's complement, that will be same as A's complement union B's complement. You can check this using the above example and verify this equality. If you look at this one, you can see that we have the complement outside the union. If you distribute the complement, you can do that by interchanging the sign from union to intersection. The same happens in the second one. You have the complement outside the intersection. If you distribute the complement to A and B, interchange the intersection to union. So this is called the De Morgan's law. So I hope that it is clear to all of you how to figure out the sample space, defining events, and by using the events and the sample space, how to come up with combinations of sets as explained in this example.